Welcome back. In today's lecture, we're going to be looking at electronic circuits, that is, entire interconnections of electronic components. You may recall in the preceding lecture, we actually looked at a particular electronic component, the resistor, in some detail. We'll look at it in a little more detail here, but we'll also learn how to represent many other kinds of electronic devices in circuits, and we'll learn how to read diagrams for circuits, and we'll learn a little bit about how to interconnect electrical systems. Let me give you an example of a complete circuit. Over here I have a board from a computer, probably a decade old by now, but it still illustrates the main idea here that we're talking about devices that are interconnected. In modern circuits, they're almost always interconnected by putting them on a board made of insulating material, and wires are etched out of copper that was originally applied to the board in a solid piece, and that's how the interconnections are made. But in the old days, they were interconnected by running wires from one component to another and soldering them together. But the point is, an electronic circuit is simply an assemblage of interconnected electronic components, a big interconnection or a very small interconnection. I have another circuit here, or part of a circuit consisting of a couple of light bulbs, and they're simply connected together by this one wire, and later we'll connect those up into another complete circuit. So we'd like to represent circuits in a kind of symbolic way. So let me give you an example of how we're going to do that. So here's a complicated looking circuit. It happens to be the circuit diagram for an audio amplifier. If it looks daunting to you right now, come back after a few lectures and you'll actually be able not only to identify the individual electronic components in this circuit diagram, but you'll also be able to kind of follow through what the circuit diagram does and what each component does. Just to give you a few examples, on the left you see an input. You see a number of zigzag structures. Those are resistors that we talked about in the preceding lecture. You see some devices with 3 wires coming out of them, or 3 connections coming out of them, and one of them has a little arrow on it. Those are transistors. You see some capacitors, and you see on the right-hand side a loudspeaker, because this is an audio amplifier. So what we have here is a language to learn, the language of electronic circuit diagrams, schematic diagrams. We could draw pictorial diagrams. I could draw a picture of a transistor and a picture of a battery and a picture of a resistor, but different resistors look different and different transistors look different, but their circuit symbols look the same. And that gives us a common language for representing electric circuits. Let me give you some other examples. Here's a much simpler example of perhaps the simplest electronic circuit, or electrical circuit in this case, that you might be able to build. This one consists of a battery, typically like a C or D flashlight battery, connected in series with a resistor, and it's a 1,000 ohm resistor. I can tell that by reading off its color code. It's a 1.5 volt battery. On the left is a picture of what that circuit would actually look like if you put it together. The white lines represent wires, which we consider to be perfect conductors. So I'll say a little bit more about that later. We ignore any resistance they might have, but there's plenty of resistance in that resistor, 1,000 ohms. So on the right, I've shown the circuit diagram, and in that diagram are 2 electronic circuit symbols. The symbol for a battery, which consists of this series of alternating long and short lines. Technically, a battery consists of several cells. This is actually just one cell, but we're going to use this symbol for batteries in general, and I'll talk a little bit more shortly about what a battery does. And that battery in this circuit is marked with its voltage. It's a 1.5 volt battery. Remember, a volt is a measure of the push that that source can supply in terms of pushing current through the circuit. And on the right-hand side, you can see connected directly across the battery is the 1,000 ohm resistor, as represented by that zigzag kind of symbol. So there is about the simplest circuit you could imagine making. A simple circuit consisting of a source of electrical energy, a battery, and a load, something to which that energy is going to be supplied. It's sometimes called a load, maybe it's a loudspeaker, maybe it's a motor. In this case, it's simply a resistor which is going to heat up with the power that is dissipated in the resistor. So what we'd like to do is look briefly at some symbols for other circuit elements. I won't introduce them all now, but I'll simply show you them, and then throughout the course of the lecture series, you'll see each of these devices introduced. So here are some common electronic symbols. We will use every one of these in this course, some of them coming much later, some of them coming much sooner. On the left at the top, you see the wiggly symbol. That's the resistor that I just introduced. We see the battery. We see a capacitor, which is not the same as a battery. It consists of 2 equal length lines with a gap between them. That reflects the electrical nature of the capacitor. Sometimes you'll see one of those 2 horizontal lines drawn as a curve, but that's still a capacitor. Next element is a diode, a kind of one-way valve for electric current. We'll be using those shortly. And on the top right is a transistor, a particular kind of transistor called a bipolar junction transistor, which is commonly used in, for example, audio amplifiers. On the bottom left is another kind of transistor that we'll have more to say about when we get to logic circuits, digital circuits in particular. Next is a transformer, a device for changing voltage levels in electric circuits. We'll be using that when we build a power supply in Lecture 4. And right after that come a pair of switches. Switches are simply devices for opening or closing an electric circuit in the simplest case of the single pole, single throw switch at the top. In the case of the switch at the bottom, a single pole double throw switch. It's a switch that can be moved to one of two different possible positions. And we'll have occasional uses for these switches. At the bottom right is a really important symbol. It's a ground symbol. And ground is a slightly ambiguous meaning in electronic circuits, but in most electronic circuits, there is a common point to which many things are connected. It's often in a battery-powered circuit, the negative terminal of the battery. In a car, for example, the metal body of the car is called ground, and it's usually, not always, but usually connected to the negative terminal of the battery. In electric power wiring, the electric power system is actually, for reasons of safety, connected directly to the physical earth ground. And outside your house, there's a copper stake, typically copper stake, driven many feet into the ground, and your electric power system is tied to ground there. I mention ground because we'll often use ground as a shortcut instead of drawing all the wires that come back to the negative terminal of the battery or the negative terminal of the power supply. Will show a ground symbol. And many circuits we'll talk about, and particularly some of the simulations we'll do of circuits in the projects, will require us to have a ground symbol in there, to have the circuit be grounded. So that ground symbol is going to be a common and important one. And sometimes you'll see it not drawn as this series of decreasing length horizontal lines, but instead as simply a little open triangle pointing down at the bottom. So we're going to deal with ground symbols. So those are some electronic symbols. Now, what we'd really like to do is to be able to characterize the electrical characteristics of all these different kinds of devices. Well, we can't do all of them in exactly the same way, but a remarkable number of them we can characterize in a similar way. And the way we're going to characterize them is by drawing graphs which show their characteristics. And I'm going to start with the battery. So I have that battery symbol again. I'm marking the plus and minus terminals of the battery. The longer bar on the outside edge is the plus terminal of the battery, and the lower one, the shorter one, is the minus terminal of the battery, and we'll mark what the battery's voltage is. And so that's a 6-volt battery, for example, and over here I have a 6-volt battery. Common battery, it's called a lantern battery. Actually consists of 4 1.5-volt cells inside it. And these two spirally wire things at the top are the two terminals. And if I look at it, the middle one, it says minus. So that's the minus terminal, and that's the plus terminal. And every battery has two terminals and a rated voltage. So the battery is one example of what's called a voltage source. There are plenty of other examples. An electric generator could be a voltage source. A so-called power supply is a voltage source. The wall outlet is a voltage source, which is a varying voltage source, as we'll see in another lecture. But a battery is a very simple example. It converts chemical energy into electrical energy, and it produces, in principle, if it's ideal, exactly the same voltage across its terminals. In the case of this one I'm showing, that would be 6 volts, regardless of how much current it's supplying. Now that turns out to be an impossibility. If we could have an ideal battery, we would have solved all the world's energy problems. I'll talk a little bit more about that later, but that would be an ideal battery. And so now I'd like to try to characterize an ideal battery by drawing a graph that shows how the voltage and current are related in an ideal battery. And as I do that, remember, an ideal battery maintains the same voltage across its terminals, regardless of how much current you or the external circuit it might be connected to is asking it to supply. For example, that 6-volt battery I just showed you is sitting on the table with nothing connected to it. It's not being asked to supply any current right now. It's supplying 0 current. But even if it were supplying 100 amperes of current, if it were ideal, it would still have 6 volts across those two terminals. So the key idea here is going to be what we call VI characteristics, voltage current characteristics. And I want to show you how we describe VI characteristics first for a battery, then for a resistor, and then as I introduce new components, we'll introduce their VI characteristics, which will be more interestingly complicated. So here's our battery again. It's an ideal battery, the same voltage across its terminals, regardless of how much current it's flowing, and I happen to have chosen it to be a 6-volt battery. So to describe the VI characteristics, I want to draw a graph in which voltage is on the horizontal axis, in volts in this case, and current is on the vertical axis, in amperes in this case. And voltage can be positive or negative, depending on which sign is in which place, and current can be positive or negative depending on which way the current is flowing. And that distinction isn't terribly important for a simple circuit like a battery and a resistor, but it becomes very important when we talk about some unusual semiconductor devices whose VI characteristics look very different depending on which way the current is flowing. So remember, our ideal battery, it has the same voltage across the terminals regardless of the current, and in this case it's a 6-volt battery, so it has 6 volts regardless of the current. So the VI characteristic curve, if you will, it's not a curve, it's a straight line of that battery, is simply a straight vertical line. Go up or down that line and you're changing the value of the current. In fact, you're even changing the direction as you go through 0. But if the battery's ideal, maintain 6 volts regardless. What about a resistor? Well, we're going to use the same graph. We're going to put up in the upper left corner a 1 ohm resistor. And remember Ohm's law, the current is the voltage divided by the resistance. That's a 1 ohm resistor. So that says if I put, for example, 6 volts across that resistor, 6 amps will flow. V is 6 volts, R is 1 ohm, I is V over R, 6 amps. So there's one point on the VI characteristic of that resistor. Here's another point. If I put 10 volts across the resistor, 10 amps will flow because I is V over R. If I put 0 amps, by the way, 0 volts across it, no current will flow. That'd be another point. If I put minus 4 volts across it in this case, put a 4-volt battery across it the other way, I'd get minus 4 amps of current flowing. And if I put minus 10 volts across it, I'll get minus 10 amps flowing. And you can connect the dots and you can see that the VI characteristic for a resistor is simply a straight diagonal line. And in this case, that diagonal line has a slope of 1 amp for every volt because this is a 1 ohm resistor. What would happen if I made it into a 2 ohm resistor? Well, 2 ohms has twice the resistance, so for a given voltage, only half as much current would flow, and a 2 ohm resistor would have the same kind of characteristic curve, that is a diagonal line, but the slope of that line is less, reflecting the fact that we get less current for a given voltage through the 2 ohm resistor. Think a minute about what a half ohm resistor would look like. Well, a half ohm resistor has less resistance than the 1 ohm or the 2 ohm. What would happen in that case? Well, in that case, I'd get more current flowing, and the VI characteristic for the half ohm resistor, 0.5 ohms, is another diagonal line, which is in this case steeper because more current flows for a given voltage. So that is the VI curves, the VI characteristics for 2 devices we've looked at now, namely a battery and a resistor. So now I want to move on, not to characterizing individual devices, which is interesting in itself, but to asking how do we connect devices together. So in fact, there are 2 important ways of connecting electronic devices, and let me define those and talk about them a little bit. So 2 components, any kind of electronic components, are in series if the current flowing through one of them has nowhere to go but into the next one. So here's component 1, here's component 2. If electric current flows through component 1, the charge that's flowing has no place to go but into component 2. And that defines series resistors. And it has to be that way. There can be no other place for the current coming out of one component to go but into the second component. If it has a choice, if there's more than one possibility, they are not in series. Okay? And consequently, because the current that's flowing through one device goes on into the other, the same current flows through both components. Now, I have to qualify that a little bit. I'm talking about circuits where things are happening in kind of a steady state. If electric charge were somehow building up on that wire between the 2 components, this would no longer be true, but that would be a very impossible situation physically, because soon a big voltage would build up and it would drive a current through the second component, and it would be the same. So when you see components in series, they have the same current through both of them. Here's a little question. Are components 1 and 2 in series? How about 1 and 3? 1 and 3. Well, look at what happens to the current through 1. It has the possibility of splitting, some of it through 2, some of it through 3. So none of those resistors are in series. There are no series combinations in that particular situation. So that's in general what series means. Let's talk now about connecting resistors in series. So here are two resistors in series. I'm labeling them R1 and R2. Current through R1 can only flow through R2, so they're in series. And without going through the physics of deriving this, and it's not terribly difficult, you can convince yourself that the series resistance is the sum of the two resistances. Resistors in series simply add. Think about a garden hose. The pressure is like the electrical voltage, the push, the flow is like the current. If you attach an extra 100 feet of hose, it's going to be harder to get water through that hose. The resistance goes up, and the same thing happens when you put resistors in series. So those are series resistors. They simply add, and here's some examples. If R1 and R2 are the same, and just call it R, then R series is simply twice R. So that is series resistors. And let me do a little bit of mathematics with series resistors over here on the big screen, because I want to describe a particular circuit configuration that's going to be really important in this course. It's called a voltage divider, and it is basically two series resistors across some source of voltage. So the battery voltage is V. We have resistor R1 and R2. We want to know what's the voltage across resistor R2. So those resistors are in series, and the equivalent resistance we've just seen is the sum, R1 plus R2. We know Ohm's law. Current is voltage over resistance, so the current that flows in that circuit, and here it is going around the whole circuit, everything's in series, same current through everything, is I equals V over R1 plus R2. Let's apply Ohm's law to R2 because we're asked about the voltage across R2. V is current times resistance. That's this current that we've just derived multiplied by R2. If I do a little tiny bit of algebra on that, I see that what happens is the voltage across the lower resistor, R2, is simply this fraction, R2 over the total resistance times the battery voltage. That's why it's a voltage divider. It divides the voltage in proportion to the resistances. And let's just take a look at some special cases of the voltage divider. One special case is when R1 and R2 are equal. In that case, got 2R down there and 1R up there, and the output voltage, or the voltage across R2, is half. The voltage divider divides the battery voltage in half. If R2 is 0, on the other hand, we get no voltage across it. It's a perfect wire. Wires don't have voltage across them. No voltage across 0 resistance. And finally, if R2 is really big compared to R1, then V2 is almost equal to the battery voltage. And I'll have a lot more to say about that in a minute when I talk about ideal batteries. R1 becomes almost a perfect wire if R2 is much bigger than R1. So that's the voltage divider, a really important configuration that we'll see again and again and again throughout this course. Okay, I have an example of a voltage divider over here. Here is a circuit consisting of a couple of resistors. Well, are they resistors? Yes, they're light bulbs, and incandescent light bulbs are just resistors. And I'm going to connect it across this 6-volt battery. And I'm going to come around and get my voltmeter fired up, and my voltmeter is set to read DC voltage, and so I'm going to read the voltage across this second light bulb, and you can see it's just about 3 volts. And we're across a 6-volt battery, and we have two identical resistors. They happen to be light bulbs, and consequently, we are good with 3 volts. We've seen that that voltage divider is working. So there's an example of a voltage divider. Now I want to take this voltage divider idea and talk a little bit about real batteries, because real batteries are important to understand. Here's how we think about a real battery. This is not really what's inside a battery, but a way to model a real battery is to think it's got an ideal battery, that impossible thing, in series with a resistor, which we call the internal resistance. You can't get inside the real battery. All you have access to are those two terminals on the end of it. And what you typically do is connect something, a light bulb, a whole complicated circuit, a resistor, whatever, across the battery, across its two terminals. The battery has some intrinsic voltage V sub 0. It has an internal resistance R sub internal. And the battery's V sub 0 is the battery's rated voltage, 1.5 volts, 6 volts, whatever it is. Rint is this so-called internal resistance. It's not really a resistor. The battery companies don't take ideal batteries. If they did, they'd solve all the world's energy problems and slap a resistor in series with them. The resistor represents rather some physical resistances of the materials the battery's made of, but more importantly, it represents the speed with which the chemical reactions in the battery can replenish charge and move positive charge to the positive terminal and negative to negative. So this is sort of a model for a battery. And now we put a load resistance across it. Again, the word load meaning what we want to supply power to. And if you look at this circuit, you'll see it's exactly like the voltage divider circuit we just had. So RL is the load resistance, and we want to know what the voltage is across the load. I connect a 6-volt battery, and I connect a resistor or a light bulb across it, and I may not get 6 volts across it. It depends on that voltage divider. It depends on R internal and R load. And there's that voltage divider fraction that we saw before. V load is that fraction, R load, that second resistor, I called it R2 before, over the sum of the resistances times V naught. And if you want V load to be equal to or approximately equal to the internal rated voltage of the battery, then as we saw when we derived that voltage divider equation, that second resistor, R2, or R load in this case, has got to be much bigger than the internal resistance. And let me give you a quick demonstration of that. Okay, so here I have a simpler circuit, just one light bulb, one resistance connected across a 6-volt battery. It's a beefier light bulb, which means it takes more current and draws more power from the battery. And there we go. The light bulb is lit. The battery seems to be doing its job well. Now I'm going to disconnect the light bulb, and I'm going to connect the voltmeter so I can read the battery voltage. And there it is, 6.1 volts. That's a reasonably healthy 6-volt battery. It might actually ought to be about 6.3 volts, but that's okay. And now I'm going to connect the light bulb across it at the same time. And you'll notice the battery voltage has dropped to 5.1 volts. It's dropped by a whole volt. That's an indication that this battery isn't doing too well, or to put it a different way, the internal resistance to this battery is high enough that we can't supply current to this particular light bulb without the battery voltage dropping, because we're losing energy in that internal resistance. Current is flowing through the internal resistance. Ohm's law says there's therefore a voltage across it. And so that battery is not working as well, has too high an internal resistance for that particular application. Now this is an old battery. If I had a brand new fresh battery, it'd probably be okay. You may have noticed a similar phenomenon when the furnace comes on in your house, or the oven cycles on or something, and the lights dim. And what you're seeing there is the same effect, but caused by extra current flowing through the internal resistance of the household wiring. And you might ask, what's different about different batteries? Here I've got a bunch of 1.5 volt batteries, a little tiny button battery, a AA battery, a C battery, flashlight battery, and a D cell flashlight battery. They're all 1.5 volt batteries. They all give charge the same amount of energy per unit of charge. What's different is the bigger battery has lower internal resistance and therefore can supply more current. Here I've got a little tiny 9-volt battery. It has a rather high internal resistance. And here's a car battery, 12 volts, not much different from 9. What's different it has a vastly lower internal resistance. So real batteries, or any real sources of voltage, have internal resistance, and you have to take that into account if you're going to use them correctly. And you have to put loads across them that aren't too low so you don't drop a voltage across that internal resistance. Here are devices connected in parallel. Two components are in parallel if the two ends of each component are connected together. So their component 1 and component 2 are in parallel, and because they're in parallel, they have exactly the same voltage across either of them. If you connected a battery across there of 6 volts, you would get 6 volts across both components. Same voltage V across both components. So that's parallel components. Are 1 and 2 in parallel? They look like they're in parallel, they're right beside each other, but they aren't, because their bottom ends aren't connected together. Component 3 comes in the way, so those are not parallel components. Parallel resistors? Well, it's sort of like adding an extra lane to a highway. If you add an extra lane to a highway, it's easier for cars to flow down the highway, it's easier for traffic to flow, and the highway offers less resistance to the flow of traffic. It's the same thing when you put resistors in parallel, the combined resistance goes down. And it goes down in a rather funny way, which again we could derive, but we're not going to bother to in this course. And it turns out that what adds is the reciprocal of the resistance, 1 over it. So 1 over R parallel is 1 over R1 plus 1 over R2. And here's an example. If the two resistors are equal, and they're equal to R, then 1 over R parallel is 1 over R plus 1 over R. That's 2 over R. And if you invert that, that says R parallel is R over 2. So if you put two equal resistors in parallel, you get half the resistance of either one. Remember, if you put them in series, you got a resistance that was twice that of either one. Okay, so two ways of connecting components, series and parallel. Not all circuits exhibit series and parallel connections, but these are easy connections to understand, and series connections in particular give us voltage dividers with that fraction we talked about. Parallel combination, by the way, is sometimes called a current divider because current coming into that combination at the left-hand picture of the diagram is coming in at the top. It can split and go between R1 and R2, and more current will go into the lower resistance. The electricity takes the path of least resistance, quote. Well, it doesn't take the path of least resistance. It divides in proportion to the resistance, and more current would flow through the lower resistance. Well, let me give you a quick quiz here. So I'd like you to take a look at this circuit. Now, it's a fairly complicated circuit. It's got 1, 2, 3, 4, 5, 6, 7, 8 resistors and a battery. And I would like you to think about which pairs of resistors are in series and which pairs are in parallel. So press your pause button and think about this for a minute. Okay, come back out of pause and let's see what we see here. You might think, well, it looks like R2 and R4 there are in series or something, or maybe, I don't know what's in series, but let's look around. I see actually only two resistors that are in series. There is only one series combination. And by the way, when you're looking at circuits, it doesn't matter how they're drawn. Series resistors don't have to be in a straight vertical line. They don't have to be in a straight horizontal line. In this particular circuit, the actual series combination is going around a corner. The resistors that are in series are R6 and R7, because if you come out of R6, the only possible place you can go if your electric current flowing is through R7. So those are in series. R7 and R8 below it are not in series because there's that path, that horizontal path at the bottom of R7, and that path could take current that way to the left as well as down through R8. So those are not in series. The only series combination in that circuit is R6 and R7. So which pair or pairs are in parallel? Well, again, there's only one parallel combination. It's the combination at the lower right of R5 and R8. You can see they're connected together at the top by that single wire, and they're connected together at the bottom by a single wire, and that's all I need to know that those two resistors are in parallel. I don't care what else is connected to that parallel combination. Those two are in parallel, and I would calculate the equivalent resistance of that parallel combination by using that formula I just described. So there's a quick quiz. It's easy to get this wrong. It's easy to look at a circuit and say, oh, these two are in series. But they aren't in series unless there's no place current going through the first component can go except into the second component. And it's easy to think things are in parallel when they're not. They are only in parallel if their tops are absolutely connected together and their bottoms are absolutely connected together. And in the case of parallel resistors, that means they have the same voltage across both of them. In the case of series resistors, it means they have the same current through both of them. Okay, let's wrap up what we've seen in this lecture. So we looked at electronic circuits as complicated interconnections of components, or simple interconnections as interconnections of electronic components. We can describe these components by graphs like we show here with the VI characteristics. We schematize the components with their circuit symbols. Components we found can be connected in either series or parallel, two possible common ways of connecting them. Series resistors simply add. Series resistors form a voltage divider with that combination of voltages, the voltage across the lower resistor being that fraction, its resistance over the total resistance times the source voltage, in this case a battery, and parallel resistors we found add reciprocally. So that's a quick summary of what we've done in this lecture, and we are now set to go begin building some simple circuits. Before we go on to another lecture, though, if you're interested, there's a project associated with this one that you can do separately. I'm going to ask you to use only 1,000 ohm resistors, but you have as many as you want. Design a voltage divider that produces 4 volts when connected across a 6-volt battery. And we'll actually use this particular project circuit, even if you don't do it, I'll describe it, in the next lecture. And here's a question now. Suppose you connect a 10,000 ohm resistor, 10 kilo ohms, across your divider between the points where you're supposed to have 4 volts. Will the voltage still be exactly 4 volts? Or if it won't, explain why it won't be and determine exactly what that voltage would be. So Lecture 2's project is a combination of design and calculate. I'm going to ask you to use only 1,000 ohm resistors, 1 kilo ohm resistors, as many as you want. Design a voltage divider that produces 4 volts when you connect it across a 6-volt battery. And once you've done that, suppose you connect a further resistor, a 10,000 ohm resistor, 10 kilo ohms, across your voltage divider between the points where you're supposed to have 4 volts. Will the voltage still be 4 volts? And if it won't, explain why and determine what the actual voltage will be. So take your time, work that project, and I'll be back with the solutions. Well, what we need is a 2-to-1 ratio of resistances because we want to have 2/3 of the voltage dropped across our bottom resistor, R2, in my description in the lecture of the voltage divider. So we really want 2,000 ohms there and 1,000 ohms for R1. Well, we can make 2,000 ohms by putting two 1,000 ohm resistors in series. So that works fine. And if we do that, there will be 4 volts across that series combination of two 1,000 ohm resistors, which functions as a 2,000 ohm resistor. So our circuit could be reduced simply to 6 volts, 1,000 ohms, and 2,000 ohms where you made the 2,000 from two 1,000s. Let's check this out with our voltage divider equation. V2 we found is the second resistor, the lower resistor, over the sum of the two resistors times the battery voltage. That's 2,000 ohms over the total, which is now 3,000 ohms, times 6 volts. That's 2/3 of 6 volts, or 4 volts. So we have exactly what we want. Now the second part gets a little harder. Suppose we connect an additional resistor of 10 kilo ohms in parallel across the 2 points where it's supposed to be 4 volts. Will it still be 4 volts? So let's give a qualitative explanation of that, and then let's determine what the actual voltage will be. Well, I now have two resistors in parallel, the 2 kilo ohm and the 10 kilo ohm, and I use the parallel resistor formula. 1 over the parallel resistance is 1 over 2 kilo ohms plus 1 over 10 kilo ohms. That's 10/6 kilo ohms for R parallel, or 1.67 kilo ohms. Now let's think about what that means. We want to know what that unknown voltage is. We could apply the voltage divider equation, but before we do, let's just note that we now have a lower resistance for our R2 in our voltage divider equation. That means we're going to pull more current from the battery. More voltage is going to drop across the 1 kilo ohm resistor, and the voltage I've marked there with a question mark is going to be lower than the 4 volts. What exactly is it going to be? Well, again, apply the voltage divider equation, now with R2 being 1.67 kilo ohms and the total being 2.67, and we get back 3.75 volts for what the actual voltage will be in that case.